Today we're going to look at the topic, section 3.9, about related rates. And one of the really cool things about calculus is that you can calculate things when they're changing or moving, not just when they're staying still. Geometry helps us get a lot of answers for items for sides of things we don't know if they're just standing still. But if we're moving, we need calculus. So that's one of the things we're going to use relateds for. So we want to look at the idea of what if I have the equation a equals pi r squared, the basic area of a circle equation. What if I want to talk about something about that circle that's changing or moving in time? And so we want to do a derivative because that's going to be talking about a rate. How fast is it changing in time? So the rate of change of the area in time or the rate of change of the radius in time. So let's use implicit differentiation, which we've already learned about, to take the derivative of a equals pi r squared. So I would call this dA over dt, since we're doing the derivative with respect to time. How fast is it changing over time? The derivative of pi r squared would be 2 pi r. And again, we just took the derivative of r with respect to time, so we'll do dr dt, just like we did with implicit differentiation before, because we need that chain rule of not only the derivative of r, but what's the derivative with respect to time. So that would be how I would use the a equals pi r squared. We'll use a formula like this in some of the equations that we have and some of the problems we have for related rates, and we'll solve for one of these unknown variables that we see. But just to practice again the concept of getting a derivative with respect to time, let's look at another equation. C equals pi d, which I know you recognize as the circumference of a circle using the diameter. So if I wanted to find the derivative of that with respect to time, it'd be dc dt. Again, how fast is the circumference changing with respect to time? And pi d would just be pi, since that would be a constant or linear, but we just took the derivative of that d, so we'll need to say dd dt. Another one, and of course we'll use all of these with more information. Right now we're just practicing how to take the derivative with respect to time. A squared plus b squared equals c squared we recognize as being part of the Pythagorean theorem, assuming that c was the hypotenuse of a right triangle. If I want to take the derivative of that with respect to t, well, the derivative of a squared is 2a, but I just took the derivative of a with respect to time. And then the derivative of b squared is 2b, with the derivative of b with respect to time. And the derivative of c squared and the derivative of c with respect to time. Another option would be, what about if it's got more variables, where we have v equals pi r squared h, volume of a circular cylinder, radius r, and height of h. If I want to take the derivative of this, then the left side's about the same as what we've been looking at. The derivative is dv dt. And the right side involves a product. So we want to think of this as the first. This is the second. So the first would be pi r squared times the derivative of the second, which is 1, because a derivative of h is 1, but we'll need to do dh dt, plus the second times the derivative of the first, which would be 2 pi r, and we just took the derivative of r, so we'll need dr dt. So we found the derivative of the product on the right-hand side using, again, the implicit differentiation with respect to time, everything over dt. Now let's try one where we work a little bit more with besides just the equation. So this time we want to let a be the area of a square whose sides have a length x, and we're going to assume that x varies with time, so we'll be looking at how things are changing with time. So it's always helpful to draw a picture of the situation whenever we can. So we're going to draw a picture of a square, at least something as close as possible to a square. Mine probably won't look exact. Use your imaginations. And then we want to label that, and each side would be x. And of course the area of that square would be a. Now the equation that relates a and x, of course, with the area of a square would be a equals x squared, the side square, for the area of any square. So we've got that equation. And we want to use that equation to find the one that relates to dA dx and dx dt. So I'm going to rewrite that what we had on that previous slide, a equals x squared. And we're going to find the dA dt and dx dt equation. So that would be dA dt, just like we practiced, equals 2x. And I took a derivative of an x, so dx dt. And remember what that stands for. That means that dA dt is how the area of that square is changing over time. X is going to be the side of the square, and dx dt is how fast the side of the square is changing. So when we get the other information from the problem, at a certain instant, the sides are 3 feet long and increasing at a rate of 2 feet per minute. We have to, on any of these related rates problem, picture a time where things just freeze. It might be moving and changing, but we're going to stop it, freeze frame, and decide what the variables are, what the values are at that moment and instant in time, which we're used to thinking about for instantaneous rate of change. So let's look at if the instant in time where we freeze is the side is 3 feet long and it is increasing at a rate of 2 feet per minute, then the 3 feet is our x value, and our 2 feet per minute, I recognize it as a rate, but what is it is the rate of? And I go back to read that it says the sides are increasing. So that must be dx dt. So if I want to use this information to plug into the equation, then dA dt, let's put the entire thing here, dA dt equals 2x dx dt. Then dA dt is what I'm trying to find, because that says how fast the area is changing. So dA dt equals 2. We said x was the side of the square, which we know is 3 feet. And dx dt is how fast the side is changing, which we've identified as 2 feet per minute. So that means dA dt is 6 times 2 is 12. And what are the units? Well, this 3 was feet. This was feet per minute. So if I multiply those, I've got feet square per minute, which is what we would expect that area would change as a square unit. So the area is increasing at a rate 12 feet square per minute when side is 3 and increasing at 2 feet per minute. I do like, my handwriting's terrible on using this little tool, but remember that we do want to actually finish in the end with a sentence that tells us what you found. What was it that you solved for and found in this equation? Another example would be looking at the radius of a circle to see that it is increasing at a rate of 3 centimeters per second, and at what rate with respect to time is the area of the circle increasing when the radius is 20. So if we think about, we look for the how fast, at what rate the area is increasing, tells me what I'm looking for, and it tells me that I know the radius is increasing at a rate, and I know exactly what the radius is. So I like to have us start with drawing some kind of picture. I think that's the best thing to start with. So we've got the radius of a circle. So we like to label it with the correct variables that you're going to be using in the problem. And then let's use the picture and what it tells us in the problem to write an equation that's going to give us something that relates the variables from the problem. So I know I'm looking at area. Area of a circle is pi r squared. So that's step 1 is the equation. Step 2, write the equation. Step 3, we want to do the implicit differentiation of this equation we've come up with, dA dt equals, we practiced this earlier, 2 pi r dr dt. So those are the equations I'm going to need to use. And let's see, but what is it I need what is it I know? What are the pieces of information that I know? I know the radius is 20. And it says that the radius is increasing at a rate of 3 centimeters per second. So I actually know that dr dt is 3. And looking back through the problem, the only other thing that I see is it's asking me to find the area or how fast the area is changing. So I need to find dA dt. So if I go in and plug in all the pieces that I know I'll need dA dt. I know 2. I know the radius is 20. And I know dr is 3. And so I already know what the answer of that's going to be is with 60 times 2 is 120 pi. And the units here, 20 was in centimeters, 3 was in centimeters per second. So I've got centimeters square per second. The area of the circle is increasing at 120 centimeters square per second when the radius is 20 and is increasing at 3 centimeters per second. So I like that sentence at the end where you kind of wrap up the information that you know.